Hi, good morning, my dear students. I'm Miss Stephanie Cole. Welcome to my channel. Spark, brilliant, inspire life. You probably first heard about the electron when you were very young, but have you ever actually seen an electron? Did any scientist see it with their eyes? The truth is, we cannot see the electron directly, but we can feel their presence through amazing phenomena happening around us. Now, let's see this simple experiment. Different salts give us different flame colors. Fascinating, right? But why does this happen? The secret lies in the electron of the salt. So, how can electron, something invisible, actually produce light and colors? In this video, I will take you through the cause of flame, the Bohr model of the atom, and the light spectrum, a scientific fingerprint of each element. By the end, you will see how something we can't see, the electron, make our world colorful and prove the beauty of quantum theory. We know the electron exists because of their effect, like flame's colors. But how exactly do these electrons produce these flame colors? To explain this, we need to look at how electrons are arranged inside an atom. This is where Niels Bohr came in 1930. Scientists have always been curious, why do some objects give out light after absorbing energy? For example, heated metal glow, and gases in discharge tube produce bright colors. Niels Bohr was the first scientist to successfully explain this phenomena using his Bohr model of the atom. Now, let's look at the three main postulates of Bohr atomic models. Let's look at the first postulate of Bohr model. So the electron move around the nucleus in fixed orbit or energy level. They do not radiate energy or lose energy. That means the electron is in stationary state, even though the electron moves, but it does not emit energy. This explains why the atom is stable. Then no energy is emitted or absorbed as long as the electrons stay in the same orbit or energy level. Orbits or energy level, or we can call it quantum levels, have fixed energy and are labeled by principal quantum number n. When the electron is in the orbit closest to the nucleus, that means the lowest energy level, we label it as n is equal to 1. So it is stable and in its ground state. For n is equal to 2, is higher energy level than n is equal to 1. So this is n is equal to 3 and so on. The energy of the electron in an orbit is proportional to its distance from the nucleus. That means the further the electron is from the nucleus, the more energy it has. Only certain energy levels are allowed, and each energy level has a fixed energy. The energy of an electron can only have a specific value, no value in between two energy levels. The electron cannot exist between orbits. Then for the third postulate, electron emits or absorb energy only when jumping between levels. When an atom is supplied with energy, like heating or electricity, an electron absorbs the energy and becomes excited, jumping to a higher energy level. This excited state is temporary and unstable. This unstable electron soon fall back to lower energy level, that means original energy level, and releasing the energy it has absorbed as light in the form of electromagnetic radiations, or we call photon. The energy released as electromagnetic radiations, or a photon, is equal the energy difference the two energy levels. The energy of the photon released is related to the frequency of the light using the following equations. For many years, scientists have been very interested in the atom. The Bohr model was important because it introduced the idea of fixed energy level. It is the first model to propose quantized energy level and contributed a greater understanding of atomic structure and quantum mechanics. It was the first atomic model to successfully explain the radiation spectrum of atomic hydrogens. Bohr explained that electrons orbit the nucleus in specific fixed energy level, much like planets orbiting the sun. These levels are quantized, meaning electrons cannot exist in between them. Bohr used the simplest hydrogen atom as it only consists of one proton and one electron. Emission light spectrum of hydrogen is produced when hydrogen gas is placed in a discharge tube at low pressure. If a high voltage is applied, the electron in the atom absorb energy and jump to a higher energy level. This excited state is unstable. So the excited electron eventually fall back to a lower level by emitting energy as light in the form of electromagnetic radiations or a photon. If you look at this light using a spectroscope, we don't see a full rainbow. Instead, we see sharp, separate lines at different wavelengths. This process produces an emission light spectrum of hydrogens. Each line here corresponds to a photon of specific energy emitted when the electron's transitions between the two energy levels. This explains why only specific lines appear in the spectrum. So, hydrogen produces only sharp lines at specific wavelengths. This experimental evidence strongly supports Bohr's postulate that electrons occupy quantized energy levels. Now, let's talk about the light emitted. It is not just one color, but light is a form of electromagnetic radiation. It is made up of different wavelengths. The electromagnetic spectrum covers a wide range from radio wave, microwave, infrared, visible light, ultraviolet, all the way to X-rays and gamma rays. But our eye only can detect a very small part of this spectrum, which is the visible regions. Let's connect this to hydrogens. Hydrogen has only one electron, but when it is given energy, this electron can be excited to higher energy levels. When the electron loses energy, it returns to lower levels. The key point is, the electron does not always fall back to n is equal to 1. It can fall to n is equal to 2, n is equal to 3, or other lower levels, depending on where the electron falls back. The emitted light has different wavelengths. If the electron falls to n is equal to 2, the light is in the visible region. This is Balmer series. If the electron falls to n is equal to 1, the light is ultraviolet. This is Lyman series. If it falls to n is equal to 3, the light is infrared, which is Paschen series. Our human eye can only detect the visible regions of the spectrum. Ultraviolet and infrared radiations cannot be seen directly by our eyes. That's why the lines in the Lyman series and Paschen series are recorded as black and white lines when detected by the instruments. But the Balmer series fall exactly in the visible regions, so we actually see this as colored line: red, blue-green, violet, and so on. Let's connect this concept to our film test. From the film test, we see different sorts give different film colors. This links back to Bohr's ideal that electrons occupy fixed energy levels. When we hit the salt, the electrons in the metal absorb energy and jump to higher energy levels, but they can't stay there. They are unstable. They fall back down. They release light with specific wavelength, and that's why we see different film colors. This connects directly to Bohr model. Electrons exist in fixed energy levels and can only move between them by absorbing or releasing energy. Let's quickly recall Bohr postulates.